So here's a great problem that lays out sort of the steps that you should be taking when doing some of these confidence interval problems. And it's just a good example of deriving the confidence interval. So the question here is, or the statement here is that the standard deviation of the weights of elephants is known to be approximately 15 pounds. We wish to construct a 95% confidence interval for the mean weight of newborn elephant calves. 50 newborn elephants are weighed. The sample mean is 244 pounds, and the sample standard deviation is 11 pounds. So we're given some information in the first part of this question. Says identify the following. So they want you to identify the sample mean, the population standard deviation, because remember sigma represents the population, and then the sample size, which is n. I want to just make this a little bit bigger just so that we can see and fill in some of the blanks here, right here on the paper. So x bar is the sample mean, which was given to us. They said it was 244 pounds, so it's this piece right here. So let's just fill this in. So that's 244. The standard deviation for the population was given here in the first sentence. So that's 15 pounds. And then the sample size was 50, and they gave that right here. So we have a sample size of 50. So in words, define the random variables x and x bar. Well, x would be if I chose just one weight from the population, and I was to just record that weight. So x is just the weight of a single newborn elephant, whereas x bar is the mean of a sample of 50 newborn elephants that are weighed. So I'm not going to write all this down. This probably take a little bit too much time, but you can see the distinct difference here. So I'll just make a note. X is a single pick, if you will, and x bar is the mean of 50 picks. So that's the difference between those two. So which distribution should we use for this problem? So one thing that we haven't really talked about in too much detail, but we have covered via the law of large numbers and the central limit theorem, is that the more samples we take, the closer we're going to get to our mean, and also the more normal that sample mean is going to be, or sample distribution of the mean is going to be. So we can assume that if it's bigger than 30, then for the sample size, then we're probably we can probably assume that it's also normal. So 30 is the magic number. So in this case, n is greater than 30. Sorry, that should be a greater sign. And therefore, the distribution is a normal distribution with a mean of 244 and a standard deviation of, now remember, we have to calculate a sample standard deviation differently than we would if it was just the population standard deviation. So we take the population standard deviation and divide it by the square root of the sample size. So in this case, it would be the square root of 50. So the next part of this question says, construct a 95% confidence interval for the population mean weight of newborn elephants and state the confidence interval, sketch a graph, and calculate the error bound. So here, the first thing that I'm going to do here is just draw the graph. So I'm going to draw it over here to the right, just to kind of keep it out of the way. And here's, that should be a normal curve. It's not drawn very well, but here's our normal curve, and here is our mean, which is 244. 244. And so we know that the mean is 244. And so now what we're trying to figure out is what is this range here that with 95% confidence we can say that any given sample of 50 will fall between. So in other words, if I took another 50 newborn elephants and weighed them and took the average weight, what would be the range that I could say with 95% confidence it would fall between? So for part 4, I'll do this in green just to kind of keep part 4 and part 5 separate. So here's part 4. So part 4, we know that the 95% confidence interval here is the interval that we're looking for. So let's say 95% confidence. So the first thing we want to do is we want to standardize. Now we could just look at this and say, oh, well, it's the 68, 95, 99.7 rule, and therefore it's 2 standard deviations out from the mean. But let's be a little bit more precise with our calculation. So if I'm looking for 95% confidence interval, I need to standardize. So let's say X bar, and remember this formula, plus or minus, we need that sort of that multiplier, that special multiplier, times, and now we need that the standard deviation of the sample, so sigma over the square root of n. Oh, that should have been sorry about that, should have been a parenthesis. So this is what we're looking for. Now, the thing, we know sigma, we know n, what we don't know is z star, or the multiplier. But we do know we're looking for 95% confidence. So if we pop over to our table in the front part of the book, you can see here that we are looking for, we're looking at this row right here, the z star row, and we're going to go over to the column that says 95, which is this column right here, and we get this 1.960 as our z star value. So I can take this now and plug it in. So X bar, and actually we don't even need to say X bar, we can actually say, let me just erase this, and I'm going to erase this as well because I don't want it to interfere with the rest of our stuff here. But we can say X bar, which is 244, plus or minus, and now we know the z-score is 1.960 from looking in the chart. Sorry, 60. Seems fat all of a sudden. And we know sigma. Sigma is 15. And n is 50. So we're going to take the square root of that. So this is the math that we need to do. And I'm going to get rid of this table here just so that we have some more room. Okay, so if I plug these into my calculator, which I have right here, you can't see it, but I'm going to plug in that 15 divided by the square root of 50. So 15 divided by the square root of 50 is 2.1213. So we'll say 2.12. So this is going to be plus or minus 1.960 times 2.12. And if I multiply that by 1.960, I get roughly 4.16. So plus or minus 4.16, roughly. I rounded up. It actually goes out several decimal places, but So this is the range. And so what this is saying is that we are, it could be either 244, it ranges from 244 plus 4.16, or let's go and start on the left. So 244 minus 4.16, which is 244 minus 4.16 is 239.84. And then if I say 244 plus 4.16, this is 248.16. And so to interpret this, I can put these up on the graph. So I'm going to put these two up on our original graph, so 239.84. And this one is 248.16. And what that's saying is that with 99% confidence, or I'm sorry, 95% confidence, I know that if I took another 50 newborn elephants out of this pack here and weighed them, the average or the sample mean would fall between 239.84 and 248.16 95% of the time. The other 5% could be, 220 or 260. They fall outside of the range, but 95% of the time I can say with confidence that it will fall between those two numbers. So the second part of this problem is saying, well, what happens if I change the interval to 500? Or what would happen to the interval if I changed the sample size to 500, which is significantly, it's 10 times bigger than what we were just working with. So we had 50, and now we're going to 500. And really the only thing that changes is that square root of n. So I can rewrite this, and I'm doing it in blue, just so that you're clear. So x bar plus or minus z star over sigma over the square root of n, which is 244 plus or minus, and now the z star doesn't change. That's still a 95% confidence. But the thing that does change is this n. And you can imagine that as n gets bigger, this number is going to get much smaller, which means the confidence interval is going to get much smaller as well. So if I do the math here, 15 divided by the square root of 500 is roughly 0.67. So here we have 244 plus or minus 1.960 times 0.67, roughly. So I'll multiply this. And your answers might be slightly different depending on what you round. Right now I'm actually plugging in a much longer number than 0.67 in my calculator, but so it might be slightly different, but it shouldn't be off by much. So I get 244 plus or minus, and I did this math right here, I got 1.31, roughly. And so what that's telling me is that it's going to range from 244 minus 1.31, which will give us 244 minus 1.31, 244 minus 1.31, sorry, just typed it in wrong here. That's going to be 242.69. And the high range is going to be 244 plus 1.31, which is plus 1.31 is 245.31. So what that tells me is that our range has now gotten smaller, So now this number here is the 242.69, and we now have 245.31. So what that's saying, and it's the same amount of confidence, same degree of confidence. So, so instead of this big area out here, now we've narrowed it down. So we're saying that if we were to take another 500 newborn elephants and weigh them and take their average, there's a 95% likelihood that it will fall. That average will fall somewhere between 242.69 and 245.31. The other 5%, they're outside of that range, but that's the level of 95% confidence that it will fall within this range. So you can see that if you increase the sample size, that the confidence interval will also decrease. So that is good because it means that we're actually getting much closer to getting an actual population mean, but we'll never get quite there, but we'll get pretty close.